CNR. She will present the gradation of cadmium yellow paints, ab initio study of the absorption of oxygen in water on 1010 cadmium yellow paint surface.
I'm Laura Giacopetti, and I'm a PhD student in Cagliari, in the University of Cagliari. And what I'm talking is the degradation of cadmium yellow pigment, ability to study of absorption of oxygen and water on cadmium sulfide surfaces, and in collaboration with my advisor, Alessandra Sotta. Okay, here there is my outline and of my talk, introduction of the problem causes of degradation, some examples, the method, density functional theory, geometric characterization and electronic structure of cubic hexagonal form, and theoretical study of interaction between the hexagonal surfaces of cadmium sulfide and the oxygen and the water, and finally conclusion. Okay, and the cadmium yellow paint is used in impressionist and modernist painting like Picasso, Van Gogh, Matisse, undergoing in several deterioration processes, including whitening and discoloration. Okay, and this alteration is due to the photooxidation process of cadmium sulfide, and is present in the paint, such as a discolored crust formed mainly by white globule hydrated cadmium sulfate and cadmium carbonate. Despite the large number of experimental analyses, the role and the origin of this white crust is not unclear. Okay, the goal of my proposal is to investigate this oxidative degradation mechanism of cadmium sulfate pigment and investigate the British compound in acrylic. Okay, and the causes of degradation are different. Chemical agents, for example, pollutant, reagent for cleaning, climatic and meteorological agent, for example, water, humidity, artificial radiation, and wind, biological agent, lichens, and fungi. Okay, and now I show you some example of famous painting. It is the still life with cabbage by James Ensor. The degradation is due to the oxidation of cadmium sulfate, and is important this detail of yellow paint surface with white globules. And I compare this detail with other detail of the same yellow in the picture, covered by the frame. But this yellow displays a more vivid yellow color. And in addition, I show you this picture, and there is the UV fluorescence investigation in whole picture in the same areas shown in panels. And another example is The Joy of Life by Matisse. The degradation is the same due to the photooxidation, but in this picture there are different degradation. There is the darkening of the yellow, there is the lightening and dirty appearance of the yellow in this part of the picture, and the lightening discoloration of the yellow fluid in the tree. The other products found in this picture are cadmium carbonate, cadmium sulfate, and cadmium chlorine. Okay, and the cadmium sulfide is present in two crystalline phases in nature, hexagonal and cubic. The amorphous form is all in all a chemical product, and the cadmium pigment is in hexagonal form and in the paint. This use of cadmium yellow is due to the high painting white applicability, ugly stability, and green yellow color. Okay, and the method used is the standard density functional theory in gradient approximation, and all detail of calculation are listed here. And the code used is quantum espresso for density functional theory, and the XPisten is the program used for visualization of crystal structure. Okay, and by means DFT, we calculate the geometry of zinc blender and bauxite cadmium sulfate, the structure of the hexagonal cleavage sulfide cadmium sulfate, the absorption energy in interaction between oxygen, water, and oxygen and water in cadmium sulfate, and the detail of the electronic structure of the interaction are given by bonding charge analysis. In this slide, I report the bulk parameters of our theoretical result, and then compare other theoretical results and experimental results, both the hexagonal and the cubic form. And you can see the argument is very good. Okay, and to simulate this surface of cadmium yellow, I have taken the hexagonal phases. I have cut it in 1-0 main, 1-0 direction for the cleavage surface, and there is in this slide the initial and the final configuration after the relax. The detail to remark is that after the relax, this profile of the surface. What happened? The cation relaxed inward to the bulk, and an ion sulfur relaxed outward from the surface. And I have calculated the surface energy, and this is our result, and is a good argument, other theoretical result using the same approach. Okay, and here there is the initial, in the particular, there is the initial and the final configuration after the relax. In the table, I report for ideal relaxed structure the standard distance in the x and y direction parallel to the surface, and that direction perpendicular to the surface. And I compare our result with other theoretical result. Is in a good argument. Okay, and to simulate the oscillation for the gradation of the cadmium sulfate, I have examined 4 distinct absorption sites. Two on top of sulfur and cadmium, and 2 hollow for sulfur and cadmium. And I have calculated the absorption energy in according to this formula. Okay, and these 4 sites absorption in this slide, there is the initial and the final configuration. And for each structure, I have calculated the absorption energy, and according to this value, we found the favorite site is on top of the cadmium. Okay, and for this reason, I study in particular these sites and the interaction between oxygen and on top cadmium. After there is the initial configuration and the final configuration after the relax. What happened? The distance don't change, and the distance doesn't change, and the oxygen move toward the sulfur, and the molecules appear to be stretched. The bond increases. And in the slide, I report the bonding charge. In this panel, there are the integration bonding charge in the plane perpendicular to the surface, plotted as height from surfaces, and I calculate the bonding charge according to this formula. In the picture, you can see the bonding charge, red area, between the oxygen and the cadmium, indicate the bond. Okay, and moreover, I studied the interaction between water and the cadmium sulfate. And in this case, the distance doesn't change, and the distance between oxygen and the sulfur, oxygen and cadmium is of order 3 angstrom, and change only the angle in the water from 104 to 103. And in this, there is the bonding charge is the same situation. There is the slight displacement of the charge, the red area between oxygen and sulfur, on top sulfur. And finally, I studied the interaction between combination water and oxygen on this surface, and the distance intralayer is the same in ideal and the final configuration. The distance is the same 3 Armstrong, and detailed to remark is the move the water in the initial configuration, the final configuration, move the reorientation toward the other oxygen. And and the bonding charge is in this area. There is the rearrangement of the charge. Okay. In conclusion, in my work, we calculated the electronic and the structure property of bulk in the surface, in the bulk of the surface. The argument with the experimental when variable and the theoretical result is very good. The interaction between oxygen, water molecules, and combination of them. In conclusion, in this interaction, these molecules appear physically, so there isn't the chemical bond. And also the bonding charge on the surface. Further analysis of the bonding charge is in progress. And perspective, I'm going to study the other surface, maybe more active in this situation, this interaction. In this case, it's cadmium sulfide nanoparticle and amorphous phases, and the photo excitation. And I would like to thank my co-worker Carla Cutrano degli Addari, the Master and Back program Fondazione Banco di Sardegna, Cineca, and the Vita.
Thanks. Any questions?
Okay, first now. Second, when you compared your simulation result with others, what is the difference? I mean, what other people use to make the same result to find out?
The other people use
Yes.
this simulation.
I'm asking you because you compared the result you obtained
Okay.
with others. What do they use?
The same approach, DFT, density functional theory. The problem is in this interaction between the cadmium surface, there isn't the experimental data. And for this, I compare only in this part of my research, only other theoretical results. But the approach is the same.
Okay, thanks.
Thank you. So, if you like to make some measurements in order to prove your calculation, what kind of measurements would you do on, for example, a very important paint without damage it?
Okay, and for paint and art in general, there is several analysis stations. And for example, to identify the morphology, the distribution, the elementary distribution, altered paint on original paint, is used in particular synchrotonic radiation in combination with X-ray techniques, X-ray reflection for identify the crystal structure. But this approach, this theoretical approach in this field is very new. Is not a lot of work in this approach.
My question is linked to the question of Sofia, because did you try to use LDA approximation, or did you use did you start to use
No,
GGA
yes,
approximation?
yes, I used the GGA approximation in all
Really, let's start to use the LDA. You start just with the GGA approximation.
Yes, yes.
Okay. Because it's present in letter.
Yes.
Because in general, usually in this case, I think that it's much better GGA in my opinion. But I don't know. Exactly. I don't know if LDA is better or not because
NDA, what does it mean?
LDA.
NDA.
And local density.
Okay.
Local density.
Because you have to calculate the local density around your cartons, your anions, but I don't know because then
No, it's better in this case. It's
GGA.
This approximation. Yes.
Okay, thank you.
Any more questions? So if not, let's thank the speaker again.
Thank you.
So we'll move to the next section.
Okay. Let's start with the section on theoretical physics. There will be 4 speakers. The first being Eduardo Bittencourt from Roma La Sapienza.
Thank you. You hear me? No. No? No? Good. No? No. So good afternoon. I'll talk about dynamical bridge. I'll move a little bit what we have heard this today. This work is completely theoretical, more mathematical than physics. More mathematics than physics in the beginning, but at the end I'll try to introduce some physics. This work started in Brazil with some collaborators from there, and also Hugo Mosquera from the University of Subria. So my thoughts divided this in 2 aspects: a kinematic aspect of the dynamical bridge, and the dynamical aspect of the dynamical bridge. What is a dynamical bridge? Dynamical bridge is a new way to describe the dynamics of a given field. So you assume a field with a given dynamic and in a given background. So you take this and map to another dynamic in the other background, but with the same field. So we change the space-time metric, and this changes the dynamics. This is in accordance with the Poincaré point of view of geometry, which is a little bit different from the Einstein's point of view. So in particular, we will focus on this kind of metric. So we have a metric which depends on your background metric, which we usually assume to be the Minkowski one, plus some tensor here that modify this background metric. These coefficients here are related such that this condition can be applied. So the product of this tensor is proportional to itself plus identity matrix. And to have a metric which is binomial, 2 terms here, and an inverse metric, which is also binomial, we have to fix A, B, alpha, and beta with according to this condition here. So this can be seen as this formal transformation. So we have a metric, and instead of do only conformal transformation, we assume some displacement here. So it can be seen as this formal transformation can be seen also as a Finsler metric, and you can find this kind of metric in several issues. So we give some examples. So we apply this kind of metrics to study a scalar theory of gravity. So my modification is given by a scalar field like this. So this is the derivative of the scalar field. So I construct a tensor like this, modification like this. I can see that the counterpart, it has the same property, and the metric is like the one I showed before. I can construct the same thing for spinors, so I take into account here the currents that I construct with the spinors. Spinors can be seen as a scalar in the space-time, but it is a vector in the inner space or in the spin space. So it has some special properties, not like a scalar, but a little bit more complicated. And the one that I will focus here, which will give orange to the geometric magnetic moment. So I have the Faraday tensor here, and I can construct my modification like this, and this has the same properties that I talked about before. So the first thing is the kinematical one. So I'll summarize our results according to this theorem. So we assume that you have a congruence of curves in a given space, and this congruence is submitted to some acceleration. So you can modify the metric of the space-time such that this congruence is now geodesic. So if from the point of view of the congruence itself, there is no acceleration. So you change the metric, and let us say the force making this congruence to be accelerated disappears. So we hide the acceleration in the metric, and the condition to do this is given by this formula here. So we have the norm of the vector in this new metric. We have to know how to transport the vector in this space. And you have here a dependence on the parameterization of the curve in this new space. So this is a very general result for any congruence in any background, and the new metric should satisfy only this equation. So an application of this mathematical result. So assuming our special metric, binomial one, so we have alpha and beta, and the inverse metric has coefficients like here. I have my congruence V. So if V has an acceleration given by a potential, mechanics or electrostatics, then the metric that I choose, okay, will relate the acceleration to its coefficient like this, according to the theorem. So I put all these things inside that formula, and I get this expression here. So the coefficients of the metric are related to the potential through this expression. So if you give me an accelerated curve in a given space, and this acceleration is given by a scalar potential, I can give you what is the metric that geometrizes this congruence. So the main difference here compared to general relativity is that you do this to all kind of fields that feel the gravitational interaction. So we introduce a universal geometry for all congruence that feel the gravitational force. So here I'm choosing only one congruence in geometrizing the acceleration of this congruence. So the context are very different contexts. So now I move to the dynamical part. Okay, a vector, I will consider only vector fields to give a concrete example for you. So I start with the Born method Lagrangian. This is a nonlinear electromagnetic Lagrangian constructed with the invariance of the finite tensor in this curved space. My curved space I call here P now. It's given as before. I have the background Minkowski plus a modification, and this modification is given by this expression here. I construct invariants in this space. My Lagrangian is given here. Beta is the critical, who knows the Born field Lagrangian? Beta is the critical field, so if you are close to this field, nonlinear effects can appear. And the dynamic of and the equation of motion associated to this Lagrange is given here. So it's very complicated dynamics in a curved space. On the other hand, I will assume the Maxwell Lagrangian, very simple, in flat space. Okay, then the equation of motion is here. The point is that to have these two theories, let us say, in different backgrounds, to be equivalent, I have to satisfy these two equations here, two nonlinear algebraic relations involving the invariants in both space and the coefficients of the metric that I choose, and the ones here. But this is general. Both representation of the electromagnetic interaction in both space are equivalent according to this equation, but I want to look in a very special case where the field is much smaller than the critical field. I will also assume that one of the invariants is 0, and this will allow me to choose a very simple metric. The coefficient of the metric will be like this, and my electromagnetic metric will be a very simple modification of the Minkowski one. So I have Minkowski here with unit coefficient here plus a modification in this regime. So one could ask that this is a very huge price to pay because you are in a nonlinear theory, in a curved background, and you are mapping to a linear theory in a flat space. How can I do physics with this? In principle, it's meaningless to use that the other point of view. So, but the point is that when we do physics, we are interested in principles and interaction. So, what can I do with a curved metric? I can assume universality, as Einstein did to the metric to describe the gravitational field. So I will assume universality of this metric. All particles, charged or not, will see this metric. Will follow geodesics in this metric. And I will assume that these particles will couple to this metric here through the minimal coupling principle. Okay, I'll use this metric here to couple all my fields to the electromagnetic field through the metric minimally. And I'll take into account only leptons for this moment. And once I'm dealing with leptons, I have to consider spinor fields. And spinor fields makes me to use the Clifford algebra to describe describe it properly. Then I have to assume a Clifford algebra in one space and a Clifford algebra in the other space, and these are the Dirac matrices. They are, of course, related because this metric has its Dirac matrix, and this metric here has its Dirac matrix. So this will be the relation in order to preserve this form of the metric. Okay. Then I'll consider my spinor field. A spinor field here satisfies the Dirac equation, a massive spinor I consider here, and the information about the metric minimally coupled to the field is here. So I'm using the usual Dirac operator to apply to the spinor, and then here I see that if the spinor sees only this quantity here, this Dirac operator in this curved space, then it's coupled minimally to the metric. I assume a modification of the covariant derivative because I can do this. The covariant derivative of the Dirac mass can be different from 0. I have here a commutating relation to this. Keeping this condition here very important to preserve the transportation of the norm of the transportation of vectors. The current is also conserved here if I compute the probability current of the spinor is conserved. So the theory in flat space, in curved space, is very well done, as I expect for a spinor field coupled to the curved metric. But now I would like to rewrite everything in terms of flat space and to see what I can get. So if I put the expression of E, gamma, and V in this equation here, okay, using all these definitions, all this stuff, then I'll get this. This is the equation of the same field in a flat space. What's the point here? The point is that we have a new term here, which is the non-minimal coupling between the spinor field and the electromagnetic field. But what is the point? The point is that we observe this interaction, but it cannot be obtained from the usual theory, from the standard model, because it's non-minimal. Standard model does not allow to do non-minimal coupling. So this can be included in the theory only as a quantum correction. So here we have explicit expression of this term. And then we are led to define what we call the geometric magnetic moment. So this quantity here does not depend on the charge of the particle, depends on the energy and the critical field. So now, how can I extend it to charged particles? So charged particles should be the total magnetic moment of the particle should be the classical one, in the case of the electron, the Bohr magneton, the geometric magnetic moment, and quantum corrections due to the charge, not to the stern limit, only to the charge. Then, compare with the experiments, we know that leptons have an anomaly of the magnetic moment. So if you measure the classical magnetic moment of the electron and divide by the experimental one, you find a difference here given by the deviation from the Landau factor. And this quantity here is tests all the consistency of the standard model. So in our case, we assume the anomaly of the mole, which is better to do this to fix the critical field because of the anomaly for the mole tests all the parameters of the standard model better than the other leptons, electron and tau. So we use the anomaly of mole. The anomaly is defined like this, the classical one, plus the deviation, times the deviation. And we make this formula equal to this one, our proposal, for the geometric magnetic moment, and obtain what would be the critical field. So this field is very high. You cannot find this field even in the crust of stars. So this is let us say, a good field to deal with. So we are not violating the postulates of the Bohr-Nymphen theory that we are using. So then once we have the critical field, we can measure what would be the magnetic moment of the electron and see if it's compatible with the experiment. So it is. So the deviation for the electron is 10 to the minus 12, and our proposal is 10 to the minus 14. So this is seen, this deviation here, then the geometric magnetic moment can contribute to the electron. But the most important point is the case of neutrino. The neutrino has no classical magnetic moment. But once you assume that it has mass, from the consistency with the standard model, it has to interact with the electromagnetic field no minimally. So it can only be done if it's proportional to the mass, which is exactly what we are saying. So we are proposing now that the origin of the magnetic moment of neutrino, if it has mass, is given by this. And on the other hand, the standard model says that this should be of the same order of magnitude. So our proposal is an alternative one to describe how can an uncharged particle classically can obtain a magnetic moment if it only if it has mass and not charge. So now I move to my conclusions. We develop a new class of geometries to describe accelerated motions in a given space as geodesic in another one. The nonlinearities of a given theory in a given space can be hidden in a nonlinear interaction in flat space can be hidden in the geometry. So we can give a geometric order for these nonlinearities. In the case of vector, we have constructed this magnetic moment through the minimal cup principle in the curved space. And then the universality a priori of the space-time geometry is left aside, and then we have to construct the physical world according to the postulates we choose. Thank you.
Thank you. Is there any questions from the audience?
Thanks. I'm curious if you can construct an alternative model of GR in this segment. So, for example, describe GR not as a geometrical field, but as the action of the star or vectorial field. So, which gives actually an effective metric, but which is actually not fundamental.
Yeah, to talk about gravity, it's not so easy in this context because the main point of Einstein theory is that you assume that gravity is geometry, and then you give the dynamic to the geometry. This second point, it's we are not assuming here. When we construct this, in this case, as you said, in this theory here. So we construct a geometry, gravity is geometry, but the geometry is not dynamic itself. So the field, the dynamic is in the field, and the field defines the dynamic of the geometry. So that's the difference. In the case of construction of a theory of gravity without a dynamical metric.
Can you use this to also construct the dynamics of the Einstein, to reproduce Einstein equation?
Reproduce Einstein equations?
So if you give the dynamics to the field which generates the metric? So now you are mapping field into metric. Can you also map the dynamics?
You mean reproduce the Einstein equation?
Yes, and effect is
why?
You can construct mechanical models of gravity.
No, I can reproduce solutions of the Einstein equations with this model, but not reproduce the dynamics of Einstein equation. Because the point is completely different because if I try to reproduce the equation, the Einstein equation are hyperbolic for the method. But here, once I already have a derivative in the field, the Einstein equation for this field will be of higher order.
Yeah, okay. Yeah. In fact, just wonder if you can turn around the idea. That's fine. Thank you very much.
Thank you. Any other question? So, if not, we can thank the speaker again. The second speaker is Giacomo Fragione from University La Sapienza in Roma, and he will talk about gravity and thermodynamics, fundamental principles and gravothermal instability.
Good morning. Good morning to everybody. I'm Giacomo Fragione from Roma Sapienza in Tor Vergara. I'm going to talk about gravity and thermodynamics. So our physical laboratory are globular clusters. This slide summarizes their characteristics and their features. They are the oldest system of stars we know. In fact, their age is of about 10 gigayears. They have a star number of about 10 to the 5, 10 to the 6, and their mass ranges between 10 to the 4, 10 to the 6 solar masses. They are spherical objects, and there are two important parameters for the definition of globular clusters, which are their core radius, which ranges between 0.3 to 10 parsec, and this is the radial coordinate where the brightness becomes 1/2 the central value, and the tail. And their tidal radius, which is of about 50 parsec, which is the effective extension of globular cluster and is due to the presence of the host galaxy. And from the velocity of the stars in this system, they are, we can see that they are not relativistic, but we can study them thanks to Newtonian gravity. Okay. So the first study is about globular clusters and their distribution function they satisfy were done by King in the 60s. King studying luminosity profiles like this. This is of Omega Centauri. He found that the most part of globular clusters followed the same empirical formula, which is given by this. And the formula was the same in its form, but changed from one globular cluster to another only due to the different concentration of stars in the different globular clusters. So this is an empirical formula, but King goes further, and in the second of his papers, he studied theoretically the distribution function of globular clusters. In fact, he said that globular clusters, their structure is given by two competing effects. The first effect is the fact that in this structure, stellar encounters are very important and tries to recover the Maxwellian distribution function of the system, but at the same time there is an escape velocity due to the presence of an host galaxy, and if a star goes beyond this escape velocity, it will be lost by the system, and it will be captured by the galaxy. And so we expect a distribution function that is about Maxwellian, but that is zero beyond the limit of the system. which is in the energy case given by the escape velocity, but that is given spatially by the tidal radius. So using the well-known Boltzmann equation of the evolution of distribution function and using the Fokker-Planck equation in the second order approximation, King obtained this kind of distribution function, where there is the first part, which is a time-dependent part, and gives us the evaporation rate of stars from the global clusters, and so the star that the system losses, and energy-dependent part of the distribution function, which is, as you can see, nearly Maxwellian minus a constant term, and zero beyond the escape velocity. And so, if we do with global clusters the same of the stars, that is, if we see in the sky different stars, we can imagine that these different stars are the representation of different ages of a single star. We can do the same with global clusters, and so we can study their equilibrium, considering that different global clusters with different potential well represents a sort of different ages of a single global cluster. The same way we do with the evolution of single stars. And so, using the Poisson equation written in this way, where W is the potential well of the system dimensionalized to the temperature, and considering the conservation of the mass, we have this graph that represents the equilibrium configuration of global clusters. And we can see that this is in function of the central dimensional potential well, and we can see that the maximum of the masses is at a typical value of W0, which is 1.35, which is important in the construction of this theory. At the same time, King did another project. That is, since this system losses stars, so the parameter describing the system evolves in time, and so the dynamics of this system leads the system itself to change its parameter during the evolution. And so, going to this work of Katz of 70s, global clusters can be seen as a sort of system in steady state of equilibrium, where during its evolution it goes from one configuration to another one, thanks to thermodynamic transformations, where the parameters of the distribution functions changes in time. And so why thermodynamics is important in this gravitational bounded system? Because the relaxation time, which is the typical time of interaction between stars, is lower than the ages of global clusters themselves. And so this means that the system forgets the initial conditions. And so this is why thermodynamics is important in this system. As expressed in these works, this distribution function obtained by King is valid, is true, until the value of 9 of the central dimensionalized potential well, and then the system undergoes due to the so-called thermal catastrophe, where there is a catastrophe and the system becomes something else. So what we did is to take the distribution function and write it in a Boltzmann-like way, but considering instead of the kinetic energy only, an Hamiltonian, which is given by 3 different terms. The first is given by the classical kinetic energy, as we do in a classical Boltzmann system. Then there is the term given by the gravitational field, and then there is this other term, which is the effective potential, which parameterizes the effect of the galaxy, which tends to capture the stars which go beyond the escape velocity, and so beyond the tidal radius of the system itself. These are the 4 characteristics of an effective potential, the most important is the fact that it reduces the space, because while in the Boltzmann case we have all phase space available for the particles, here we don't have it because we have a limiting velocity. Then the effective potential depends on the energy of particles on the radial coordinate, and goes to infinity to the energy corresponding to the escape velocity. So in the case of the distribution function of King, this is the mathematical form of the effective potential, and it splits the thermodynamical variables into different variables. The first ones are variables that we call thermodynamical variables, that are simply mathematical variables. Are variables similar to the Boltzmann distribution function, and so they have the same, as we will see, they have the same characteristic of a Boltzmann gas. Then, at the same time, the effective potential reduces the phase space, and so the so-called kinetic variables, which are the physics variables of the system, don't have the same meaning of the standard thermodynamics as we see in the next steps. And so, using the standard definition of the thermodynamical variables, we have these two kind of different set of variables, where the kinetic ones are given considering only the kinetic term of the Hamiltonian, as we do usually in the classical Boltzmann thermodynamics, and while the thermodynamical variables are given considering the full Hamiltonian, which is given by the three terms we saw before. And here the chemical potential is a gravothermal potential. So considering this radial dependent variable, which links the two set of different variables, and considering what we do usually in classical thermodynamics, so linking the intensive variable to the extensive conjugate, we can recover the first principle, the Gibbs-Gunn relation, the Euler equation, the equation of states. But we have two of them, one for kinetic variables and one for thermodynamic variables. So now I will show you the difference of these two kind of variables. First of all, so we can study the equilibria in our system. Now, since we have a system with a gravitational potential, so a system where it's important also the radial coordinate, we have two kind of different variations of our variables. The first one is the thermodynamical transformation, and another one variation is due to the movement along the radial coordinate of the system itself. And so, as it is usually done in thermodynamics, we can study the three different equilibrium. So, considering always the condition that the differential of the total entropy is equal to 0, considering a thermodynamic transformation between two consecutive shells. And so in the first case, when we study thermal equilibrium, we recover for the thermodynamic temperature theta that it is equal to 0 along the system, as it is usually the temperature in the case of Boltzmann. But if we see the kinetic temperature, it is not constant anymore. It depends on the position in the system. It depends on the potential. And this is because, as we saw, the distribution function is 0 beyond the escape velocity. And so we must have a profile of temperature which must go to 0 at the border of the system. The same is for the chemical equilibrium, where we have the thermodynamical chemical potential, which is constant along the configuration, while the kinetic one is not constant. And finally, the most interesting thing is about the chemical equilibrium, where we recover, we have for the kinetic pressure that we have from our equation, not imposing it, the hydrostatic equilibrium. It comes out from considering both thermodynamics and gravity in this system. Now, an important parameter for describing the systems and the revolution towards the gravothermal catastrophe is the specific heat. For example, considering a very simple case where the gravitational potential is zero, but not zero the effective potential, we have this profile of the specific heat. And as you can see, when W goes to infinity, the gravity is not important anymore about thermodynamics. We recover the value of 1.5 of the Boltzmann gases. While the question is more complicated if we consider also the presence of the gravity, and we can see that we have a profile in our system of the specific heat. And this depends, as we saw for the configurations, from the central value of the potential value. And so we can see a very important thing that the core, given by the radial coordinate at which brightness becomes 1/2, as seen in the first slide, is always a specific heat region. While the total specific heat is negative only for value W0 higher than 2.3. And so this is the same graph scaled to the core radius. And as we saw, there is this value very important on 1.35, where there is a transition between systems that have always positive specific heat and the system that have a positive core and a negative region around the core, as we can see also in this plot. Studying the energy, we can see that the energy is not always negative, but the energy can be also positive. This is positive for value of W0 lower than 3, and for value between 2.3 and 3, we have negative and positive energy regions. So I summarized these plots in this picture, where we can see what we obtained, and so we can see that if the value of W0 is lower than 1.35, we have only a positive system. So the system can evolve towards the gravothermal catastrophe, which is given by the exchange of heat between negative and positive specific heat regions. And at the same time, for system with W0 lower than 3, they evolve towards disruption because the energy is positive, so they are not bounded systems. Now, all this can be applied to data analysis, and I reported here the work of my colleague Vidantoni, where we have here the data analysis done by Peterson in the 70s. And here the graph obtained with the linear series method of Poincaré. And so we can see that Peterson saw that the mean of distribution is at the value of W0 of 6.9, while we have that the stability range is between 0 and 7.4. And so we don't expect this because global clusters are very old systems, and so we expect that they have had much time to evolve towards disruption, which is given by this value 6.9. And so now, considering a new catalog given by Ellis in his paper of 1995 and 96, and doing the analysis with not a Gaussian hypothesis, but with a symmetrical Gaussian, we can see that the mean of this distribution is always 6.9 as Peterson saw. But the stability limit is between 0 and 6.9 thanks to the introduction of the contribution of the effective potential. This is not a strange contribution, this is simply the contribution of the effect of the host galaxy, which tends to capture the stars of the global clusters. And this is given considering the total energy, where we have not only the term given by the kinetic energy thanks to the classical Euler theorem, but also this contribution in energy. And so then putting on the diagram the empirical point given by these black points, we can see that these points follow quite well the new curve of data. And so, as conclusion, I can say that this model is a self-consistent model, and because I have negative and positive specific region. Instead, previous work, as in the case of the famous work of Lindenthal and Wood, had external part of it. Then the fact that the core is a positive specific region could justify the fact that we can see also post-core collapse objects that are objects that underwent the geothermal catastrophe, and so we can see something in the sky after this catastrophe. And at the same time, the difference outlined by Katz seems to be resolved thanks to this introduction of the effective potential. As perspectives, I can say that first of all, this model is very simple because it is not multi-mass, and so we should put into the theoretical model a spectrum of masses, and the effects of binary stars formation are not taken into account. At the same time, one should also study the contributions of gas velocity, which are not seen in today observations, and also try to perform anomaly simulations in order to see if theoretical calculations are confirmed. And finally, one could also try to construct thermodynamic ensembles of standard thermodynamics, considering the Newtonian made up of the three fields I showed you before. And that's all.
Thank you, Giacomo. Is there any question from the audience? Mine, okay. So you already presented some comparison with experimental data.
Yes.
And what do you think about other experiments performed? So maybe my question is very naive.
So this, first of all, I want to say that it is not my work, but
okay.
I said by my colleague, and this is points given by the data of the catalog of events. And so here there is a bias in this total energy that is given by this effective potential that up to now is only a theoretical calculation of this potential. So we should try to do observations which gives us a measurement of this potential, also the potential of the galaxy in way it acts on the system. And so up to now this is a quite well concordance between data and the plot. Okay.
You mentioned that you want to apply this to the binary star formation.
Okay.
Do you have an idea if it could be applied for the coalescence of binary stars? There's any thermodynamical contribution to this?
Yes, in this case, this is one of the perspectives because one should add this contribution to the theoretical model, because when there is the coalescence of binary stars, some gravitational waves are emitted, some heat is emitted, and so this could modify the collapse of the system itself. And so this is a very important, I think this more important than considering a spectrum of masses, because masses in global clusters don't range in a lot. So this is the main thing we should improve in
the in principle, you can measure this coalescence easily than star formation. You have a lot of pulsars and you can compare this with the data easily than the data of star formation.
No, I don't understand.
I think it's easy to to compare this theoretical approach to the data if you see the coalescence, because you have a lot of pulsars.
Yes, yes, I should improve this theoretically, and then my colleague will try to improve it experiment in the data analysis.
And can you go back to the diagram, the experimental diagram? I was just wondering, since you mentioned something about taking into account, for example, the binary systems and so on and so forth. I see that in the lower right-hand side corner, there is a huge spread around the curve. Do you think that the fact of this thing you didn't take into account may spread the curve as well and explain this spreading of
this spread of the data is expected because this point, okay, is the limit of the stability. So I expect that after this point we have a spread because systems will undergo to the catastrophe. So I don't expect they follow the distribution anymore. So I expect they follow another one distribution or another one theoretical model. And so this is expected.
I see. Okay, thank you.
Grazie. Thank you. We can thank the speaker again.
So just one technical message. We received a request, so is someone going away from Trieste by car towards the southern part of Italy? No. Okay. Thank you.
I go to Genoa, but I don't know.
The next speaker is Enrico Baldi from University of Parma, and he will talk about modeling time-varying networks with memory.
Can you hear me? No. Should work. Nothing. Can you hear me now? Can you hear me? Is it on? Okay. No. Okay. Can you hear me now? No. Okay, so can you hear me now? Yes? Okay, good. Hello everybody, and thanks to the organizers for the given opportunity to speak here at this conference, this meeting. And today I will talk about my latest work. It is model time-varying networks in memory. And this is a model developed and data-driven, which means that is let's say, inspired by data, by real-world data sets. And since we are speaking and dealing with networks, let me introduce the basic features of the networks. I will keep it very simple. So in networks, we have nodes. In social networks are people, like us. And these people are called nodes, vertices, or peers, as however you want. And these people are connected by ties, or links, or edges of the networks. Okay? So every person has a certain degree, that is the number of people he or she knows, or she is in contact with. And on this topology, that is the first important thing of the network, and it is the thing I will focus on in this talk. On this topology, it goes undergo different dynamics. For instance, collaboration, scientific collaboration. I publish a paper with someone, or even phone calls, or opinion exchange, basis spreading, etc. So it is important to understand, measure, and characterize how this topology evolves in time and how people connect to each other, with how with the processes undergoing this topology evolution. And in fact, these dynamics in general, will take place on an evolving topology. That means that not all the connections are available at all the times, and some of them will be like unavailable for some moments, or they will reappear, etc. And so that's why we have two main frameworks to describe networks. The first and the classical one, the most common one, is the static or quenched networks framework. Here, the topology, it is the connection, evolves on a time scale, on a characteristic time that is way larger than the dynamics. Think about the internet. The connection between two servers is there for days, months, years, maybe, but to send an email or to send a chat message, it just takes 1 second, if not less. Okay? So this is the classical point of view. It's good to describe technological, infrastructural network, and so on, solar network, cloud network, etc. But this, as you can imagine, is not a good model to model social interaction, because in the social case, interactions are done continuously, are created, deleted, and so on, because I can meet with you, and then in 5 minutes I meet another person, I call someone else. So in the social case, we have a complication between connection and dynamics are now strongly coupled, okay? And here we see an example of the so-called time-varying networks. We have 3 slices, 3 temporal snapshots of a network, of a time-varying network. As you can see, each time slice is totally different from one to another. The nodes are connecting and interacting through connectivity patterns that are completely different from one time step to the other. In fact, if we keep in the last picture here the integrated network, we can see that this network is completely different from the singular slices, from the singular snapshots. Within this time-varying network framework, there is a new paradigm recently developed, that is the activity-driven paradigm, where each node is given an activity. That is like how likely is for a node to get active and call some other nodes. Okay, think about the activities as the number of phone calls I made, or the number of emails I sent, etc. So this new paradigm is good to describe social interactions, such as the spread, online social networks, microblogging, etc. So now we introduce the first ingredients, the switch, the switched focus from static to time-varying networks. And now we should focus now, what one usually does, is to focus on the evolution of the so-called econet. That is the neighborhood of one node. That is the friends of one single node, how we contact these friends, how likely it will be to contact a new friend, and how this set of friends evolves in time. So as you can imagine, it is reasonable to expect that we will have to introduce some kind of memory in this process. So from a random and memoryless process, we have to switch to a non-Markovian dynamics. That is, we have to introduce memory. The memory can be introduced in many ways, in several methods, and we decided to measure memory as a transition rate, like a Pn, a probability n. That is the probability for a node that already contacted n people, n different people, to get active, then contact a new person. So to switch from a degree n to a degree n plus 1. This probability, once we insert it in a network evolution, strongly modifies the characteristic of a network. Here on the top, we see a network that has been evolving with a random attachment process. That is, each node, when it gets active, can call a randomly chosen node in the network, and we see that after very few time steps, we have fully connected networks. We don't have isolated nodes or something like that. We have some hubs, the yellow one here, but nothing more, nothing special. Instead, if we plug in an attachment probability that in a certain way imitates the creation of new nodes, of new links, we see that this network, with the same time steps, with the same time of evolution, is now very sparse. We have very few connections, mainly localized on the neighborhood of the most active nodes, and the network is completely different also from the topological point of view. And so even the dynamics will be affected from this new characteristic of the network. So since we are dealing now with a data-driven model, as I told you, let me introduce the dataset that we used in this work. We have the American Physical Society co-authorship network, that is the physical review ABBEL from first edition to 2007. So all the papers, the person that published the papers, how they collaborated. Then we have the Twitter fire hose for 9 months in 2008. Fire hose means all the users, all the activity of the users for 9 months of Twitter. This is pretty huge. This is pretty small. It's like 1 month of 100,000 people for a Yahoo chat, Yahoo Messenger. And then we have another huge one, 7.4 million users for 3 months of a mobile company in an undisclosed European country. So all these datasets are features, some characteristic peculiar of real-world data and real-world datasets. That is like a very broad distribution, power law distribution of the activity. That is again the propensity of a node to interact with some other, to, for instance, publish a paper or make a phone call or tweet a message. So we have a lot of people very less active and few people amazingly active. Okay, so a power law distribution of the activity, as well as a power law distribution of the degree. That is the number of friends. So we have a lot of people with very few friends and few people with a lot of friends, more than 200 here in the table. Given this heterogeneity, to study and measure the memory, we decided to group the nodes first based on their activity, thus defining activity classes, and then within an activity class, we further divide nodes depending on their final degree K. Okay, so we define DA classes, but this is a subgroup, don't worry about it. The fact is that if we measure the memory for activity classes, that's what comes out. So here we show the four data sets, and we show only one activity classes. So nodes that more or less perform the same amount of social interaction, of social calls. And this is the probability for a given degree n to attach to a new people, to a new friend, to contact a new friend. For some nodes, this probability, as you can see, quickly drops to 0, even for small n, or like less than 10. And for other people, like this one, this probability is still close to 1, even for large degree, so like more than 100 friends. So given this functional form and this very heterogeneous behavior, we decided to propose the functional form here in the box. So a probability of attachment that depends on the being class, and that is like 1 over 1 plus n to the power of some beta. That is like a memory strand. In fact, the larger the beta, the quicker will be the decrease of this curve. Okay, and this beta will be, of course, distributed in this network because, as we see, there are very different and very diverse behavior within this network. So once we put this prediction on our data, we find a nice agreement, between the data and our functional form. And now it is worth asking how this memory is distributed among the nodes in the network. Okay, so we evaluate the beta, and we see how this beta is distributed amongst all the activity classes. Here on the X, we have different activity classes. Okay, and in the red box, the total distribution for the total network, for all the nodes in the network. And on the Y, we represent the distribution of the memory strength in one single classes. Okay, so we have here two remarkable results. The first is that this distribution, the P of beta, seems to weightly depends on the activity. So nodes that have very different activity values will behave more or less the same from a point of view of memory. And the other remarkable result is that the same functional form and the same behavior is found for all the datasets analyzed. Okay? We find for all the cases with independent activity, memory strength distribution with activity, and software. So now, by grouping all these ingredients, we can actually develop a model that is an activity group that is within the activity-driven framework. We give to each node a potential A, an activity A, that is the probability to be detected. When once a node is active, you can shoot M links. We set n to 1, and so we have an activation whether the nodes get active or whether it gets called by another node that is active. So, of course, the network will have some characteristics that I won't present now. The important thing is that we introduce also the memory with the attachment probability that we outlined before, but so far with a fixed beta for all nodes in the network. This is a pretty important point, with a fixed beta. Once we write the master equation that I won't present in details, we can solve it, and the master equation focuses on this PAKT, that is the probability for a node of activity A to have degree K at time t. Okay? In the long time limit, the solution is like a Gaussian in K, and the average value of this Gaussian grows as a power of time with the exponent depending on the memory strength beta. That, remember, is defining the attachment probability. So now that we have a solution, it is worth testing it against numerical simulation. We find a nice agreement between the long time limit of the numerical simulation and the predicted shape of this distribution. And now here we have a map between the degree K and the activity A of a node. So we can also predict the degree distribution at the inner power evolution time based solely on the activity distribution and on the memory strength beta. Moreover, we can also predict the growth of the average degree of a single activity class in time for all the simulated set of parameters, let's say. But now we have to go back to the real world, and the first huge difference is a heavy tail in the PAKT that is not at all predicted by our model. Okay, so this, despite the fact that we can actually catch more or less the shape of the peak of this distribution, we cannot at all predict this heavy tail of the PAKT for large degrees. One possible explanation is that, well, we inserted in the model a single value of beta, whereas we saw that in the real world we have a very distributed beta. So what happens if we put by hand a beta distributed as in the real world in the simulation? Well, we observe like a small rising of these heavy tails, so maybe this is one of the causes, but this is still under discussion. However, the important thing is that if we compute the average beta, the beta bar, that is the average value of the memory strength over all the activity classes, we can still predict a lot of things, like with a good accuracy as well, like the mobile phone call datasets here. We can predict pretty well the growth of the average degree for the activity classes with this average beta, and also we can predict here the degree distribution, the slope of the degree distribution in the final time for the PRL and physical UL vector datasets. Okay, so just to conclude, we show and we introduced an attachment rule that correctly describes the EcoNet evolution in real-world social networks. We introduced and solved an activity-driven and more convenient generative model. The fact is that we still miss some key features of the networks, some local features like communities and clustering, and we still have to characterize the dynamics, so like how this memory, how this evolution of the network affects like disease spreading or rumor spreading or information spreading or epidemics. And before finishing, let me thank the people that I've been working with, my statistical physics group at the University of Parma, Professor Milioni and Tani, and the MOPS lab in the Northeastern University in Boston, where I had the pleasure to work with Professor Spignani and Nicola Perra and Marco Cassano. Thank you very much.
Is there any question for the speaker? No? So I have one. And it's a curiosity actually. So we are, for this meeting, we try to do a network of researchers. What I'm thinking is if some of your quantities, like I don't know, the number of connection between researchers, can be used as a sign, not of equality, but maybe of the activity of a node or no.
There are some works done in the field to measure actually the rise of some new research topics like neuroscience or something like that. That actually see you can see from this data two communities of scientists that are working, and then they meet at some point because the new field is born, and they begin to interact a lot and form a new community. That is now the neuroscience community that comes from complex systems and, for instance, biology or neurobiology, etc. And about the quality, we are working, well, the future work should be like to understand how the citation network goes. So there's some like yeah, proof of quality for the works that one publish, but I don't know how we can apply it for this conference.
Another question is you show the tails of the distribution for Twitter. That means that there is a probability that it is higher with respect to what you expect from the theory for large case, large degrees. So meaning that the probability to get a new friend for a people that already has a lot of friends is higher.
Still higher, yes. But the fact is pretty amazing because here the curve is already scaled with the average degree of the class, as you can see here.
Okay.
So you have actually people with 20 times more friends than the average people with that activity. So it's really a heavy tail because it's okay, it's going down like an exponential or something like that, but I mean 20 times the average person.
So it's the expected behavior and it's the meaning of the local society.
Well, the meaning is we think that this distribution of the number is starting. I mean, you have, let's say, the same amount of social interaction as me, but you can spend them better, let's say, without memory, randomly, by choosing all the time new people. Like, I didn't say it, but there is a paper now that says that actually there are two kinds of people, like two at least, that are social keeper, that is, people that are connecting and interacting always with the same little set of people, and social explorer, that are the guys in the tape, who continues to attach, regardless of the friendship size, to new people. So the famous people that have like 2,000 friends on Facebook or something like that.
Probably, for sure you know about the population model. If you fix like the probability, you get the second or the phase transition. But this probability is not, well, it's not fixed, so it's like dependent on the degree. But can you go back to the definition of the?
Okay, the attachment rule, like this one, right?
Yeah. So, do you know if there's also like a phenomena like phase transition if you tune the beta, like you get in population theory?
Okay, we didn't actually try it yet, also because it depends on how long you let the network evolve. Because you can put also a very large beta, for instance, so you limit the creation of new edges, but if you let the network evolve for like 10 years, let's say, there is a probability that all the network gets connected, right? And yeah, actually we are watching the prepositioning problem from an epidemic point of view to see how the epidemics will spread on these networks. But I'm not sure if I got the
Yeah, no,
That's all right.
and if you look at the degree distribution, it's like a small ball. I mean, up from your connection probability, you might end up after a specific time in a small ball, right?
Mhm.
True? Or, I mean, did you, when you look at your degree distribution, it's like from a small world because it's scale free.
Yeah, it's scale free.
Yeah. So, okay, yeah.
Well, we can discuss it offline.
Thank you. We can thank the speaker again.
So, so
the speaker is
Fulvio Spisa from University of Milano and University of Portsmouth. And he will talk about critical tension in the 6D cascading DGP model.
So hello, thank you for being here to listen to me. My name is Fulvio Spisa. I did my PhD in collaboration between University of Milan and University of Portsmouth. And today I will talk about two papers actually I did in collaboration with my supervisor, Kazuya Koyama. So, okay, I will skip this. Right. So, let's say 15 years ago, more or less, we have a quite clear picture of how cosmology works. So we have three different hypotheses. One is that the universe is homogeneous and isotropic on very large scales. The second hypothesis is that the universe is filled by matter, which is ordinary matter, like standard model matter, plus total matter, which you need to explain some phenomena in galaxies, for example. And then we assume that general relativity is the correct theory that describes gravity. So this was a very good framework because it explained very well several experimental facts, like for example the abundance of light elements that exist on the CMB, the Hubble's law, for example. And however, you can see from the second Riemann equation, you see at the bottom that in this framework, the acceleration of the scale factor is always negative because for ordinary matter and cold matter, the energy density is always positive and pressure is always non-negative. However, like in 98, 99, a breakthrough came with the observation of supernovae data, which seemed to point out that the universe is actually accelerating with a positive acceleration. Now, this has been confirmed since then by several other experimental observations. So now we have a quite good evidence that the universe is indeed accelerating. You can see that this is completely impossible if we assume the hypothesis we used to have like 15 years ago. So for sure, at least one of them has to be wrong. So you can say that isotropy is very well tested around Earth, but homogeneity is not, because we cannot move away from Earth. So you can just relax homogeneity, and you can think that the Earth is at the center of the huge spherical void, and consider the metric term on boundary metrics. Or you can assume that the back reaction of the fluctuation of the metric actually influences the evolution of the scale factor, and we are actually misinterpreting the data. If you instead think that homogeneity is a good assumption, then you can assume that the universe is filled also by an extra degrees of freedom, which can be the cosmological constant, or can be dynamical, like dark energy, for example, quintessence and k-essence. However, you really don't observe in the lab this degree of freedom. So if you don't assume that there is no dark energy or cosmological constant is zero, then the only way out you have is that to consider that the observations are actually pointing out signaling that gravity is actually not a good description of gravity at very, very large scale. So a breakdown of gravity. For example, you can have one models of massive gravity of brain waves. I consider in my thesis the modified gravity approach because, I mean, cosmological constant is in some sense the most obvious option, most natural. However, it has several problems. First of all, maybe just a classical second scale of gravity. However, you see that the universe is very fine-tuned in the sense that in cosmological history, the moment where structures tend to form and the moment where acceleration wins is very, very close. And this is completely unexpected because in principle, the two facts are completely unrelated. So you need a very fine-tune to reproduce this characteristic of the universe. On the other hand, you expect a term of the cosmological constant type as a semi-classical manifestation of vacuum energy. However, if the predictive values from theory differ from the observation by a huge amount, between 16 and 120 orders of magnitude, depend on the cutoff of the theory. Of course, there may be both a bare and a semi-classical contribution to lambda, but still you have to fine-tune very, very precisely the cancellation between two explained observations. So it may be indeed that modifying gravity to large distances is a good way to study and to solve these problems. However, there are some issues. In general, if you modify GR, you introduce new degrees of freedom. And these degrees of freedom necessarily will be observed in fifth force experiments or in the dynamics of in astrophysical dynamics, unless they are screened. There are several screening mechanisms like Weinstein mechanisms, Cameron, symmetron, and so on and so forth. Another problem is that quite often, at least around some backgrounds, this perturbation modes has negative kinetic energy, so they are ghosts, like the Ball-Desert ghost in massive gravity. So a ghost is a very bad thing to have in a theory because it means that the vacuum is completely unstable, it's a catastrophic instability. Actually, I read a small review on this problem. If you are interested, see at the end of it. In my PhD, I consider a model which is called cascading VGP, which is a brainwall model. So in these brainwall models, our universe, four-dimensional universe, is thought to be like a four-dimensional surface embedded in a higher dimensional space. And in particular, in this case, we have a recursive embedding of brains into brains. So you have a four-dimensional brain embedded in a five-dimensional brain, which is again embedded in six-dimensional block. There are two free parameters, and you see that weak gravity cascades in some sense. So from large scale to small scales, it behaves six-dimensional, five-dimensional, four-dimensional if M6 is much less than M5, or it cascades directly from 6D to 4D in the other case. Also, this model is very interesting because usually if you have a codimension 2 brain, so a brain which has dimension 2 less than the ambient space, gravity always diverges when the brain is thin. So in this case, it does not happen. The brain regularizes gravity. And also there is it has been proposed that there is a critical tension you can put on the codimension 2 brain, such that if you have lower tension than the critical tension, you have a ghost in the theory. However, if you put enough tension, the theory becomes healthy and ghost-free. So this is not very well understood. It was not so. Our idea was to try to understand geometrically why this critical tension emerges in this theory. And one of the problems is that if you consider the two brains to be thin, then the theory is not well defined, because it has been proved already in the 80s that if a brain has codimension more than 1, then its thin limit is not well defined. So we had to choose a regularizing procedure, and we chose that to impose a hierarchy. So we chose to impose the fact that the codimension 1 brain can be decided to be very much thinner than the codimension 2. So you can consider a thin codimension 1 brain and like a ribbon brain embedded inside. we actually did, what we did in practice was to study perturbations around at first order and around these pure tangent solutions. And we left all degrees of freedom, so both the bending of the brane and the metric degrees of freedom, free to fluctuate. This is geometrically more suited to the problem. However, there is a problem of gauge issue, so you have to make sure that you get rid of unphysical nodes. So what we did is to consider for this scalar vector tensor composition and use gauge invariant variables. Actually, you can reformulate the whole theory in the scalar sector, for example, in terms of master variables. So two variables are enough to describe the whole system. One is the metric degrees of freedom, which I call pi, and the other is delta phi orthogonal, which is the normal component of the bending of the codimension. So in general, these 2 degrees of freedom obey a system of a couple differential equations, but if you consider just the codimension 2 brane, you can eliminate the bending and just obtain a master equation for the pi field. However, this master equation still contains normal derivative. So in practice, to compute the evolution of pi, you have to solve the whole CDV equation, so you don't have a really simplification. So we consider a 4D limit which decouples the codimension 2 brane from the codimension 1 and the bulk. And what you did is to get this simple equation, which is basically box 4 is proportional to the trace of the energy momentum tensor. However, the kinetic coefficient is very strange and lambda dependent. And you can actually see that there is a critical tension when this kinetic coefficient changes sign. And from this equation, you can actually reconstruct the properties of pi, and you find that it is an effective ghost if the tension is less than the critical tension, or it's a healthy field above. So we actually reproduce here the results of the literature. We also gave a geometrical interpretation, which was actually missing in the literature, why this critical tension emerges. So and actually it turns out that if you put energy momentum on the brane, this excites the pi field via 2 very different channels. So it does so directly because the 4-dimensional induced gravity term couples the metric on the brane to the energy momentum tensor, and does so in a ghostly and lambda independent way. And then there is another channel. So if you put energy momentum on the brane, this makes the codimension 2 brane move. This induced movement of the codimension 1 brane. The movement of the codimension 1 brane is coupled to the pi field by the 5D induced gravity term. And in the end, you get that the competition between these 2 effects originate the critical tension. And basically, the most effective of the 2 channels decides if pi is a ghost or not. There is actually a mismatch with the literature because the result we found is different from the result that was already known in the literature. And the 2 results are quite similar if you consider, for example, M6 much smaller than M5, but are completely different in the other case. And this difference is not only an academical problem, but it's very important because in our case, so I have to say that there is a maximal tension you can put on the codimension 2 brane. So if you put the maximal tension, which I called lambda m, the geometry becomes ill-defined. So you can only put tension less than the maximal tension. In our case, you see that lambda critical is always smaller than lambda maximum. And therefore, so it is always possible to choose a lambda such that the theory is ghost-free. So for every value of M6 and M5. Instead, in the result of the Ram, Khoury, and Tolley, you have that this is true only if M6 is small compared to M5. In all the other cases, you have ghost anyway in the theory, so the theory is phenomenologically excluded. So actually, it's important to understand which of the 2 results is true, because if the second result is correct, then half of the parameter space you have to throw it away. So it's not to understand who is right and who is wrong. We first identified the source of the difference. So the dynamical equation in this system are the bulk equation, which are the Einstein equation. you have to add to them the Israel junction condition on the codimension 1 brane. And if the codimension 2 brane becomes spin, you have to complete this equation with a codimension 2 junction conditions. To obtain this, you have to perform a pillbox integration across the codimension 2 brane, and then send the thickness of the brane to 0. So it turns out that our paper and the paper of Dharam totally do this in 2 different ways, which do not agree. So we decided to test this by considering a thick codimension 2 brane and do the pillbox integration numerically. So there cannot be confusion. There's no assumption behind this. You just do the integration numerically. And you do this for sequences of thickness, and then you study the asymptotical, how it behaves asymptotically. Of course, to do this, you have to know the structure of the internal structure of the brane as well as the external structure. That's why we consider a very particular kind of perturbation, so a pure tangent perturbation of the brane. In this case, the internal structure is exactly solvable. So you can actually do this, perform the integration numerically, and then compute and compare the result with the lineage model. And so this is the result we got. So you can see the numerical result is indicated by the circles. So the parameter n, which you see on the horizontal axis, is a parameter which is inversely proportional to the thickness. So when n tends to infinity, the thickness goes to 0. So our result is indicated by squares, while the Dharam-Fourier-Tolly results is indicated by diamonds. And you see that asymptotically, when the thickness goes to 0, our result indeed converges to the numerical one. Instead, the other result does not. This tells that, at least for pure tangent perturbation, our result is correct. And puts our analysis on a firm footing more in general, not only for this kind of information. So I will summarize the results and what I did so far. So first of all, brainwaves are a very powerful scenario to tackle the late time acceleration and both the cosmological constant problem. So in general, you can try to tackle either one or the other, but with brainwaves, you can just try to solve both of them, actually. The cascading DGP model seems promising to solve at least one of the two. However, the singular structure of the codimension to brane is very, very subtle, so the pillbox integration has to do very carefully. As a future direction of this work, you can, since we did an analysis of first order perturbations, of course, it's necessary to study the ghost problem at nonlinear level to see if the ghost disappears or remains, and also perform a Hamiltonian analysis to see if the ghost is in independent degrees of freedom or not. So if it is not in independent degrees of freedom, maybe not a problem even if it exists. More in general, you would like, so this model has been proposed in 2007, but it's not well studied yet. So there are a lot of things to do. For example, derive the codimension 2 junction condition at non-perturbative level, study the Weinstein mechanism, which screens the exit degrees of freedom, study cosmology, so cosmologic solutions are not being derived, and so on. So this is it. So thank you very much for the attention.
Thank you. Any question?
I don't know if there are in literature comparison between the same theory with, for example, data from Planck on the data set, and if your model can be compared to the data in order to see if.
No, it cannot, because so you see that cosmological solution has not been derived yet, so you cannot produce. So once you define cosmological solution, of course, you can compare to data and do everything. But so far, it's a pretty new model, so it's very complicated actually to find tomorrow solution. This is of course a work we would like to do in the future, but so far it's not been done. So you may argue that why do you consider it all this model, because it has a cosmological, in some sense, reason to exist. The fact is it is very difficult to tackle this the cosmological constant problem and the late time acceleration problem. So you try to sometimes you instead of try to fit the data, you try to go to construct a theory which has the desiderable properties, and then try to see if it fits the data. So this is still to do.
I'm not an expert in this, but in general, with the brain theory, you introduce spatial dimensions. It's possible to introduce time-like dimensions.
Yeah, you can. So time extra dimension has some problems, because if you have an extra time dimension, so two time dimension, one is the hour time dimension and an extra one, you can construct closed time-like geodesics. So, and you have violation of causality and so on and so forth. So it's a very sorry.
In this extra dimension.
So if you have just one time dimension, everything is fine. But if you have one time dimension and one extra dimension, then you can construct these closed time-likes.
That's out of the space-time.
Well,
Dimension space-time.
yeah, but you can go away and then come back. No? So it's it is a problem. I'm not saying you cannot find a way to conclude that, yeah, you have violation of causality, but they are not observable, maybe. But in principle, it's a very, delicate thing.
You consider the Israel condition to join the brain to the, can you consider other kind of joint conditions?
So
some of them are not equivalent.
Why would you want to consider other? Because the idea behind brainwash theories usually is that gravity in the bulk is described by Einstein's equations in 6D in this case, or in 10D or whatever. So the Israel junction condition is not something you put by hand. They come from the Hilbert's integration of the Einstein equations when the brain is spinning. So the Israel junction conditions are basically another way to say that gravity is described by higher dimensional Einstein theory.
When you, in the end, you say that you want to tackle like the accelerating universe problem, and right now there are like theories where you include the inflation as well as the rate expansion in the scalar field. When you get rid of all your bulk dimensions, in the end, can you do you end up with the scalar field theory, or is it?
Okay, so well, I think you were referring to like unified models, which you explain all the acceleration. There is a scalar field which produces acceleration like in quintessence, something like that.
Yeah, I mean, in the end, you get somewhere you have to reduce the dimensions if you want to come up with where we already are. I mean, how to do compactification? I don't know how to call it.
Right, like I said. So in this case, you don't need to compactify the space because so usually if you put a brain with Einstein gravity, then gravity does not behave four-dimensional, it behaves higher dimensional. So you have to compactify the external space in order to have 4D gravity. However, in this case, there is the induced gravity term you put in the actions causes gravity to be four-dimensional anyway. So it's not like in the Randall-Sundrum model. In the Randall-Sundrum model, you have 4D gravity without compactifying space, just because you put tension on the brain and the bulk is anti-de Sitter. So in this case, the induced gravity term does all the jobs. He it produces four-dimensional gravity, even if the bulk is not compact. So if I can say something about the expansion of the universe and the acceleration, in this kind of theory, like brain-induced gravity, so as I said, in this model, cosmology is not understood yet. But for example, in the DGP, the original model, you can find exact cosmological solutions. And there are two branches of solution. One is, let's say, the conventional branch. So in Europe, you use basically the cosmology and then it behaves slightly different. However, the second branch is self-accelerating. So just for geometrical reasons, the evolution of the universe behaves normally, and at a certain point, it starts to accelerate and asymptotis at the center phase, just because of the structure of the geometrical field. So, and actually, what I said is not completely correct, because just one solution, cosmological solution in the sphere, has been derived. So we know that self-accelerating solution exists in this theory already. The problem is that you don't know what happens before, because you don't have a generic cosmological solution, just at the center. So you have to understand what happens before, if the solution is stable, for example, and so on. So I don't know if I answered.
Other questions? So if not, we can thank all the speakers of this section. Thank you for your contribution in these 2 days. And now we can have an official wrap up.
From me then. Very official. So maybe also the other people with the red badge can come. Okay, so I think those were 2 very interesting and full days. I hope you enjoyed them at least as much as we did, because I mean the contributions were all very interesting and relevant, and all the quality of the talks was very good, not only from a scientific point of view, but also from the speaking point of view. I mean, all of you were very involving and entertaining, and it was never boring to listen to you. So, very good job. So the first thanks goes to you, because you were here, and your interest and your support in following us made it possible. Then there is a lot of other people I'm supposed to thank, so I'll try to go through it as quickly as I can. So the first biggest thank you goes to CISA for supporting the event, for hosting us for the 2nd year in a row, for believing in the project, and at all kinds of levels, at financial level, scientific level, administrative level. So for this, I need to thank Professor Martinelli for whatever he did on listening to us and not chasing us away multiple times we went to bother him for ask for help. Professor Salucci and Professor Petkov and the group of Statistical and Biological Physics from CISA also supported the meeting. So we thank them and acknowledge their help and support. University of Udine, and in particular Professor Marina Koval, also gave a very strong help for the realization of the meeting. And so we are very happy not only to have them as our sponsors, but to having been in touch with them, and we do hope that this collaboration and their interest in the meeting keeps on also in the following years. We want to thank also the group of solar physics from University of Roma Tor Vergata, in particular Professor De Lilli for being with us not only this year but also during past editions, and this year for giving a very concrete support for the publication of the proceedings. So this is very important to us, because I mean, as this is a fee-free conference, we are relying completely on the support of the sponsors, and we try to do our best to save money and still to give the best service that we can, but we need money, so okay. after this very ugly sentence, we can say, now it's up to you. Would you like to bring a meeting to one of your universities? Do you know funding agencies that are willing to invest on young researchers? Then this is your moment. You can come to us and tell us your name and your email if you're interested. I guess you have received a couple of emails by us. Maybe some of you have received some communication, so you know where to contact us. We have a wonderful website. We will send you a survey for how much you enjoyed the meeting, which you will fill in with everything. There is a deadline, unfortunately, for those of you that want to publish the proceedings, so news will follow on that. And last but absolutely not least, I would like to thank the support of MediaLab, technical support, emotional support for the workshop led by Simona yesterday that I think all of you enjoyed, and for the streaming that both last year and this year helped us in providing, so you can watch again and again and again all the talks until our channel goes down for too many visualizations, so use your power wisely. And so, okay, I don't know if someone wants to add something to this very long sproloquium. Thank you, Matteo.
Yeah. So we can say our names and emails now? No. They know, okay.
No, you can write at secretary.
Secretary is always open.
Yes, not always.
When I'm on the internet. Okay.
Okay, so
we can go for
thank you really. So now we have two choices. First choice is leading a very interesting scientific discussion about all the contribution that we have listened to, or having an informal but still significant discussion outside in front of the last coffee break. Okay. So see you next year and stay tuned for next event.